Welcome to the second lecture of module 1 in this course low voltage CMOS circuit operation. So, the first module is explaining the MOSFET operation in weak and moderate inversion regions, which is important for low voltage circuit operation. So, today in this lecture we will finish the basic review of MOSFET operation which we are doing in this course. So, we will discuss regions of operation. So, first we will discuss quasi-Fermi level using which we explain the electron and hole concentration in different parts of the device. And in the previous lecture we had seen for VDS is equal to 0 how the carrier concentrations vary in different regions of the MOSFET. In this lecture we will see what happens when the drain to source voltage is not 0. So, quasi equilibrium condition is also not valid, and we will discuss charge distribution, and we will discuss in different regions of the device what are the electric fields, electron hole concentrations, etc. And we will then discuss the surface potential and with respect to regions of operation of the device. So, what is this idea of quasi-Fermi level? This quasi-Fermi levels we use to estimate the carrier concentrations, electron and hole concentration in different parts of the device. So, in non-equilibrium condition, when the device is not in equilibrium condition. And as we had discussed, a MOSFET, if the drain to source voltage and body voltage are 0 and you change the gate voltage, the silicon region or semiconductor region of the MOSFET device would be in quasi-equilibrium condition, where the semiconductor region of the device would function as if it is in equilibrium condition. Quasi-Fermi levels of electrons and holes, they do not separate, and they locally they would act as if equilibrium condition is there and you are dealing only with Fermi level which you are used to. So, what are these quasi-Fermi levels? So, if the semiconductor is in steady state condition, that is roughly you can think as if the electron and hole concentrations in the conduction band and in valence band respectively are constant. So, the device is not in equilibrium, there is an exchange of energy with the outside world. So, the device is not in thermal equilibrium, but steady state has been achieved. The electron and hole concentrations in different parts of the device are steady, constant with time. So, in such a case you can define quasi-Fermi levels, which are mathematically using which we can estimate the hole concentration in valence band and electron concentration in the conduction band. So, this is based on a few assumptions that the Maxwell-Boltzmann distribution, which we Fermi distribution reduces to Fermi Dirac distribution reduces to Maxwell-Boltzmann distribution whenever the semiconductor is not degenerate, that is the Fermi level is not within the conduction band or valence band. So, that we had seen in the prerequisite courses. So, in case there is steady state and there is no equilibrium. So, you cannot estimate the electron and hole concentration using Fermi level, the idea of Fermi level, because the hole and electron concentrations are now, because of the external energy exchange, the hole and electron concentrations are now not at the equilibrium value. So, in non-equilibrium, so the law of mass action is not valid. NP would be a constant if it is steady state. But it would not be equal to Ni square. So, therefore, the Fermi level as we define in equilibrium condition would not be valid. But the basic assumptions of Maxwell-Boltzmann distribution, that the particles are distinguishable and the total energy of say electrons in the conduction band, it would remain constant because there is a steady state and the entire system has an energy exchange with the outside world. So, it is in non-equilibrium condition, but there is steady state. So, the electron concentration in the conduction band is constant, hole concentration is also constant. And there are other assumptions of Maxwell-Boltzmann distribution, like the available energy states are far the available energy states far outnumber the number of electrons in conduction band. So, these other assumptions of Maxwell-Boltzmann distribution are also valid. So, the statistics would follow similar mathematical expressions as in the equilibrium condition, because locally within the conduction band all the assumptions which led to Maxwell-Boltzmann distribution being valid are again valid locally within the conduction band for electrons and locally within the valence band for holes. So, therefore, a similar mathematical formulation would work. So, our mathematical formulation in equilibrium condition was that we said electron concentration where EF is the Fermi level, EI is the intrinsic level. Okay. So, a similar expression would now be valid. So, you have non-equilibrium steady state So, so this is what results. So, within the conduction band you would have the electrons following a similar mathematical expression with the Fermi level being replaced by a quasi-Fermi level of electrons, because the assumptions behind Maxwell-Boltzmann distribution are valid locally within the conduction band. So, likewise within the valence band the hole concentration would follow the Maxwell-Boltzmann distribution with the Fermi energy being replaced by a quasi-Fermi energy of holes. So, and what is this difference F n minus F p? So, that in further lectures we will call it QV and you will see the significance of that. So, where Q is the absolute value of an electron charge and V is some potential difference, some voltage. So, this Fn minus Fp is Qv in this case. Okay. So, it could be negative, it could be positive. If you are dealing with a depletion region, then N and P are both smaller than their intrinsic values. So, then V would be negative. So, if you have some injection of charges, suppose, so in that case N and P could be larger than their equilibrium values, then V would be positive. So, this is a brief introduction to quasi-Fermi levels. Now, let us look at the MOSFET when drain to source voltage is not 0. So, when drain to source voltage was 0, there was no current from the source to drain, and there was no current within the device. So, this silicon region was in a quasi equilibrium condition. So, what happens when drain to source voltage is non-zero? So, silicon region is also now not in quasi equilibrium condition, because the carrier concentration would vary along this line B prime, and if there is a carrier variation in carrier concentration, there would be diffusion of carriers, and also electric fields are developed in the x direction, y direction here. There would be carriers which would be flowing. So, quasi equilibrium condition is not there in the silicon region, but a steady state could be achieved after a so if you switch the drain voltage high, suppose from 0. So, there would be some disturbance, and after a while a steady state would be achieved, and once the steady state is achieved, you can work with quasi-Fermi levels. So, that is what we are doing here. So, this is, let us look at this orange band diagram. So, this is conduction band and this is valence band. These are the quasi-Fermi levels. So, now you are looking at a part at the channel which is very region which is very close to the source, the channel region which is very close to the source. So, if you apply a VDS non-zero positive VDS here at the drain, at the source there is 0, the 0 volts which is applied. So, the potential here would be, so suppose initially you are in equilibrium, quasi equilibrium condition where VDS was 0. So, now you increase the value of VDS. So, in the channel at the edge of the source, the potential would remain similar to what it was, same as what it was in the equilibrium condition. The potential would change only in the channel near the drain and anywhere within the channel, but this part of the channel which is closest to the source is tied to the source electrically. So, there the potential would remain at a value which is determined by the source. So, I am talking about the point which is closest to the source region. So, in some sense you are dealing with part of channel which is at the edge of the theoretical kind of edge of the source and the channel. So, here the potential is the same as what it was before VDS was turned non-zero. So, that is where we are looking at the band diagram along the vertical line A prime. So, that is the part of the channel which is closest to the source. So, if suppose with the applied gate bias, the band diagram looks like this. So, here you have Fp Fn. So, in equilibrium condition, the quasi-Fermi levels of source of electrons and holes were aligned with each other and matching with each other. That is because there was no electron or hole current in any direction, and in equilibrium kind of within the silicon there was an equilibrium kind of condition. So, and we are saying at the source end of the channel the condition is same as that of the equilibrium. So, here we are not applying any body bias is also 0. So, at the source edge of the channel the condition is the same as what it was in equilibrium. So, therefore, the quasi-Fermi levels of holes and electrons would align and match each other in equilibrium and in quasi-equilibrium, and therefore also at the along the vertical line A prime. So, along the vertical line A prime, the quasi-Fermi levels of holes and electrons would align with each other. Now, you come to C prime. C prime is along a vertical line which is closest possible to the drain. It is within the channel, but it is close to the drain. So, there you have applied a potential Vd. So, suppose you have applied a potential Vds here. So, to support this Vds, there would be a larger, the depletion charge would be larger near the drain. So, support this larger value of channel potential here at the drain edge of the channel, which is Vds now. The depletion charge would be larger at the drain edge of the channel, and that would, so if the depletion charge is larger, what happens to the potential drop along the channel from the neutral P region till the edge of silicon and silicon dioxide? What would happen to the potential drop? The potential drop would be larger, and therefore, the band bending at the along the line C prime is larger, as we can see within the silicon. So, it is larger. What happens to the quasi-Fermi level? So, for this we first need to understand what happens, what is the way the quasi-Fermi level. For this, we first need to understand the quasi-Fermi levels in depletion regions. If we look at this channel, suppose this is inverted. So, if this is inverted, you have high electron concentration along this line B prime, which is close to the silicon dioxide interface, and very high hole concentration in this neutral P region. So, if we look at this current density of electrons, current density of holes, we know that it is proportional to hole concentration locally, and so it is proportional to the hole concentration and its product with the rate of change of whole quasi-Fermi level along the direction in which you are looking at the current density. So, along the z direction, it is given as shown here. Now, as you move downwards from A to A prime, what happens to the hole concentration? It increases significantly, exponentially in negative z direction along A prime. So, in that case, since P is increasing exponentially, if Jp is constant, then since P increases exponentially as we move from A to A prime, dFp by dz would reduce drastically, as you would reduce very fast as you move along A prime, from A to A prime. Otherwise, Jp cannot be constant, and we know that Jp is very small. The current density of holes is a very small value, and the current density of holes would more or less be constant for gradual channel approximation. So, here we are dealing with gradual channel approximation. So, as you so the electric fields in the y direction are negligible compared to the electric fields in the z direction. So, that is essentially the gradual channel approximation, and it is valid for long channel devices. So, in when gradual channel approximation is valid, the whole currents along A prime direction would the current density would remain constant, because the whole current is almost unaffected by horizontal electric field, that is the electric field along direction y or x. Okay. So, due to this, even if we consider that Jp is non-zero, but it is then almost constant along A prime direction. So, P increases exponentially as you move from A to A prime along A prime direction. So, dFp by dz should become almost negligible as soon as you enter the depletion region from the interface and towards you are moving towards A prime. We had seen in the first lecture that with a very little change in the potential in depletion region, the carrier concentration, hole concentration in this example would increase exponentially. So, a little change in potential along A prime direction would translate to a small distance. So, as you move slightly into the depletion region, you would find that the whole concentration increases at a very rapid rate. So, therefore, what we essentially would like to say is that the whole quasi-Fermi level would stabilize. So, whatever is the whole quasi-Fermi level position at the interface, as you move slightly into the silicon vertically, you would find that the whole quasi-Fermi level would become constant, and it would therefore align with the whole Fermi level or whole quasi-Fermi level in the neutral P region. So, therefore, we draw the whole quasi-Fermi level to be constant within the depletion region. What about electron quasi-Fermi? Now, at the along line A prime, which is close to the source, now suppose the device is inverted, strongly inverted. So, there is a high electron concentration here, but the electron concentration is very low in the neutral P region. So, as you move along A prime towards A within the depletion region, the electron concentration would increase exponentially, as we had seen in the first lecture. So, as the potential increases, the electron concentration would increase exponentially. And what is the relation governing this? We had seen in the first lecture. So, it is where chi is the potential here. This is what we had seen, isn't it? So, and 0 is the potential here. This we had seen. So, now it is increasing exponentially as you move into the depletion region. So, therefore, if electron, and because of the reason going through an argument which is similar to that which we went through while discussing whole concentration or whole quasi-Fermi level along this line A prime, using similar arguments, we can say that the electron quasi-Fermi level would become horizontal as you move along the depletion region from A prime to A, okay, and it would align with the quasi-Fermi level in the high electron concentration region. So, therefore, since there is almost 0 electron current density in equilibrium condition or in quasi-equilibrium condition, and it is almost like quasi-equilibrium condition at the source edge of the channel, the quasi-Fermi levels of holes and electrons would align and match at the interface, and we are saying that the quasi-Fermi level of holes would be horizontal as you move towards the bulk, and quasi-Fermi level of electrons would be horizontal as you move towards the interface. So, therefore, both the quasi-Fermi levels would match with each other and would remain horizontal all along the depletion region from bulk to the silicon dioxide interface at the source edge of the channel. What happens at the drain edge of the channel? Now, let us see what happens at the drain edge of the channel, that is along the vertical line C C prime. Now, suppose you have applied a voltage V as VDS. So, with this voltage applied, the potential uh, potential of the silicon dioxide interface increases by a value V compared to that at the drain edge of the channel. Potential at the silicon dioxide interface here along this line C C prime increases by a value V compared to that at the source edge of the channel, that is along C C prime the potential increases by a value V compared to that along A prime. But suppose the channel it is in strong inversion and the channel is present at C C prime. So, if we suppose that the channel is present at C C prime as well as at along A prime. So, in that case, what would happen to the quasi-Fermi levels and the band bending? As you can see here, the band bending along A prime from bulk to the silicon dioxide interface, suppose it was some value 2 phi f, we will come to 2 phi f later again. At the drain edge of the channel, that is along C C prime, it is now 2 phi f plus V. So, as you can see, it is 2 phi f plus V. This has now increased. So, at the source at the edge of channel, if it is 2 phi f, at the drain edge of the channel, that is along C C prime at the interface, it will be 2 phi f plus V, because the drain voltage VDS is now V. So, the band bending would have to be from body to the silicon dioxide interface, it would have to be increased by QV in such a case. So, that is what we are showing here. It has increased by value QV compared to this. What happens to the quasi-Fermi level of holes? So, along this vertical line C C prime, the hole current, again there is no reason for the hole current to be significant or to change its value if gradual channel approximation is valid. So, there is no reason for it to change its value along line C C prime from C prime to C. So, therefore, our earlier argument that the quasi-Fermi level of holes would remain horizontal from bulk to the silicon dioxide interface would again be valid along C C prime also, because the same argument runs. What about electron concentration? Now, suppose the channel is inverted, we will relax this condition of channel being inverted from B to B prime, but right now let us consider that channel is inverted from B to B prime. Then electron concentration, as you move into the channel, as you move into the depletion region from body from C prime towards C, you would find that the electron concentration exponentially increases as you move towards this interface, as we had discussed in the previous slide. So, if it exponentially increases, then the electron current, which is proportional to n would what about the electron current from C prime to C? So, electron current, if gradual channel approximation is valid, electron current from C prime to C would be negligible. So, in that electron current density and would also be constant because gradual channel approximation is valid. So, in that case, as you move from C to C prime to C, since n increases exponentially, dfn by dz would be near 0 as you move from C prime to C. Okay. So, therefore, the quasi-Fermi level of electrons would be horizontal as you move into the depletion region, but as you move from B to B prime, you find that at A prime the quasi equilibrium condition kind of band diagram was valid, and when you moved here towards to C prime, you find that the surface potential has increased by a value V. So, if it has increased by a value V, then and we also see that the quasi-Fermi level of holes is horizontal from the and aligns with that of the quasi-Fermi level in the neutral bulk region, and the quasi-Fermi level of electrons would remain horizontal from the interface silicon dioxide interface, and it should align with that at the interface. So, and we have increased the potential at drain. Suppose there is strong inversion all along from B to B prime. So, in that case the band bending from B to B prime would also correspond to QV, isn't it? And electron concentration, as we know, the electron concentration is given by this, and EI at source edge, that is along A prime at the interface, minus EI along C prime at the interface would be QV. If this is QV, and electron concentration would have, if there is channel inversion from B to B prime, the electron concentration would be quite large at near B, as well as it would be quite large near B prime. There is an inversion charge all along. Suppose the inversion charge changes, the value changes by a certain value. So, the change in Fn would be negligible comparatively. So, there is a certain change in n as you move from B to B prime. The corresponding change in Fn minus Ei would be negligible because of the exponential relationship. Okay. So, therefore, virtually we would see that Ei minus Fn would almost not change when you move from B to B prime, that is from the interface at along A prime to the interface along C prime. So, when you move from the interface along A prime to the interface along C prime, you would find that there is virtually no difference in Fn minus Ei. There is a negligible difference in Fn minus Ei, very small. So, therefore, this is the quasi-Fermi level at the interface along A prime. So, if Ec minus this value has a certain value along A prime, then Ec minus Fn at the interface along C prime would also have almost the same value. So, therefore, the quasi-Fermi level of electrons would have moved down by a value qv from where it was at the interface along A prime to the interface along CC prime, and therefore, Fp minus Fn at the interface along CC prime, that is at B prime, would be qv. So, what would be the carrier concentration at the interface? So, that let us try to estimate hole concentration. What is the difference between quasi-Fermi level of hole and the value of EI now along CC prime at the interface? The band bending has increased by a value QV compared to that along AA prime. So, if along AA prime it was suppose 2 phi f, so the band bending has increased by a value V. Suppose it was 2 phi f at the interface along AA prime, that is this. Then at CC prime it is now 2 phi f plus V. So, therefore, and the quasi-Fermi level of holes has remained the same at the same value. So, therefore, the hole concentration would now reduce by exponentially with QV, because the band bending has increased. So, the difference between the quasi-Fermi level and EI would increase by a value V. So, that is what has happened. So, if we see the hole concentration along AA prime, then it is again coming back to the electron concentration at the interface in along the line CC prime. So, that would be this NP is the electron concentration in the body. So, that is in the neutral body. This has not changed. Why? Because the quasi-Fermi level has also moved down by a value QV. You could have seen this as Ni exponential Fn at the source edge minus plus QV minus EI at the source edge plus QV by KT. You could have seen it this way. So, what would be the corresponding electron concentration at the source edge? Yeah. So, these are things which we will use as we go along this course. Based on our discussion till now, if we look at the band diagram along the line B prime, which is very close to the silicon dioxide interface, you would find that it looks like this. So, Fp would remain constant, as we had discussed, Fp would remain constant all along the channel, because it is aligned with the bulk quasi-Fermi level, bulk hole quasi-Fermi level, and therefore, it would remain constant horizontal all along from B prime to B. But what about Fn? If the entire channel is from B to B prime is inverted, then as we had discussed, Fn would almost move along with Ec or Ei. So, that is why Fn would see a similar bending to as that of this. So, therefore, the drain edge of the channel Fp minus Fn would be Qv, as we had discussed earlier, because this is V. So, therefore, Fp minus Fn at this edge would be Qv. Okay. So, that is what we are seeing here. Now, let us look at what is the value of electron concentration anywhere along the channel. Suppose you have a horizontal line here, some d prime d. So, along this, suppose the potential here is chi and the potential here is at the interface, silicon dioxide interface, that is surface we call it, it is chi s. Here it is 0. So, let us see what is the value of electron and hole concentration at any arbitrary value z, at any arbitrary value of z within the channel depletion region. So, it is so chi is the potential at z. So, what is this? And what is Ni? As we had seen earlier, Ni is therefore, you could have written N as what about P at a value? What about P? This is because we are using the approximation in the neutral bulk region, the hole concentration is equal to the acceptor ion concentration Nb. So, now let us write down Poisson equation. along the direction z. So, again we are looking at this line which is d prime, and we are looking at a point z where the potential is chi. What is this equal to? The total charge. So, what is total charge comprising of? So, n electron concentration at z so electron concentration at z plus so minus plus the whole concentration at z minus Nb. So, there are these acceptor ions all along the channel, and we are considering them to be uniform now, right now. So, negatively charged acceptor ions into electron charge, absolute value of electron charge divided by the permittivity, which we call epsilon silicon for short. So, actually it is, so this epsilon silicon for us is epsilon naught epsilon silicon. So, this is what we are replacing with epsilon silicon, just to be brief. So, what would this be? This we can write down as the same Poisson equation we can write this down as based on our previous discussion. At the source edge, it would be this would stand for N, this would stand for P, and this for acceptors. So, suppose we are not at the source edge of the channel and we are along this line d prime. So, since our z, so we are on this line d prime. Suppose there is a surface potential is V here, it is 0 here, and the potential increases by VDS here. So, here it increases by some arbitrary value V at along d prime, it increases at the interface by an arbitrary value V. So, at the interface, how would we write this same expression? So, as we had seen earlier, now the electron concentration would reduce by a factor V. That is what we had seen earlier. So, as you can see, the electron concentration does not reduce by the same value as the whole concentration. As you move from d prime to d, the electron concentration does not, it reduces by a factor chi minus V, e to the power chi minus V by ut, whereas the whole concentration this increases by this factor. The whole concentration reduces by a factor e to the power minus chi by ut. So, here you have this subtraction of minus V also, which is minus QV, which is coming. That is because the electron quasi-Fermi level has also moved down by QV, as we had discussed earlier. So, that is why this minus V term also appears here. Okay. So, you are at some point V here. So, the quasi-Fermi level has also moved down by QV. So, here you have e to the power minus chi by ut, here you have e to the power minus chi minus another V term appears here. Okay. So, now if we look at this, we could have written this as we could have written it this way, or we could have written it as or in other words we could have written it as so using this we rewrite the expression. Or we could have written it as so if we integrate, so what is the electric field deep inside the bulk here, so it is 0, and what is the electric field here, it is the interface electric field whatever is its value. Let us call this as the interface electric field. So, how do we integrate this? What the potential we are defining it to be 0 here. We are defining the potential to be 0 here, and it increases at the beginning of the depletion charge, and it becomes chi s here, surface potential. So, what do we get? This is what you get. So, now if we look at this, this is because of the electrons contribution, and this is because of the holes, the contribution. And this is because of the ions, acceptor ions in this case, dopant ions. So, we could have written this as, if we look at Debye length, so it is defined as So, you could have used this to rewrite this. So, this expression we obtain. So, as we have seen, the first term is because of the electron concentration, the second term is because of holes, and the third term is because of the dopant ions. So, and this is the interface electric field. So, we will use this expression to further understand the electron hole concentrations and surface potential, their relationships in different regions of operation in the next lecture. So, in this lecture we have discussed quasi-Fermi levels and the relation of electron and hole concentrations with change in potential and quasi-Fermi level in semiconductors, and we have also seen solved Poisson equation and related the electric field at the interface with surface potential (Is). So, in the next lecture we will see how the electric field and the surface potential vary in different regions of operation of the device.